Hello, welcome to episode 8 of Stats with Mats, once again from the Panic Room. Today, I want to give you a couple more opportunities to practice Chi-square, two examples that are going to actually demonstrate one of the weaknesses with Chi-square and introduce then a statistic called Cramer's V, which we will use to evaluate the strength of the association, whether it's there or not, in order to overcome this inherent weakness of Chi-square. So that's the agenda today. We'll do two Chi-square formulas and then get in on Cramer's V. Today's dumb movie commentary comes about A Few Good Men, which is an absolutely fantastic movie, and it's been replaying. It was replaying quite a bit over the weekend. Actually, BBC was playing it, and some other station had it. My commentary on this is in defense of Demi Moore's character. Joe Galloway. I always remember being a very common thing to conceptualize Joe Galloway as a bad lawyer because she makes one pretty serious screw up in the midpoint of the trial. However, let's not forget that she's the one with the idea. She has the entire idea to put Colonel Jessup on the stand and to goad him into essentially admitting that yes, he did order the code red, and you can't handle the truth. So let's just not lose sight of that's literally the winning strategy of the trial, and Tom Cruise was not brave enough to do it without the urging of Joe Galloway. So yeah, she's a good lawyer. Let's get into the material today. Chi-square, you will remember, is something we use to determine whether or not you have a significant relationship between two categorical variables. If all you care about is trends, then that's great. Just eyeball it and say what the data is telling you. But to say whether there's evidence of the effect of an independent variable upon a dependent variable requires inferential statistics. And that's the chi-square formula, which you will remember is defined as the summation of the observed frequency minus the expected frequency squared divided by the expected frequency and then summed across all 9 or whatever, across however many marginals or cells you're actually operating with. And you have to calculate the expected frequency by multiplying the percentage in the overall population for that group by the total category group size, right? So we took the percentage of overall Republicans and multiplied that by the raw number of Christians, Muslims, and Jews. And that gave us exactly what we needed. Okay, so here's my next problem that I want to work through. The General Social Survey asks people, compared to other people your age, how would you describe how healthy you are? Now, this is a really important variable in the social determinants of health in public health research because, believe it or not, self-rated health actually predicts mortality and it predicts hospitalizations better than doctors' reports do. How could that be? How could we predict this better than doctors? Well, maybe it makes a little more sense if I explain that one of the reasons for this is uniquely American. Self-rated health does not predict mortality better than doctors' reports in Europe, but it does here in the United States. And the reason for that is because Americans are known to lie to their doctors, like all the time. We tell our doctors we're exercising. We tell our doctors I'm only smoking a half a pack a day, even though you're smoking a hell of a lot more. And so as a result, how you feel, your doctor can only go off the information that you give your doctor. And he or she is able to make a judgment based off of that information. But the term here is really garbage in, garbage out. If you give your doctor bad information, you're going to get bad medical advice as a result. Anyway, so here's what we've done here. A sample of 100 people. We are classifying people into a very simplistic ordinal measure of age status, either young or old, and a very simplistic measure of health, good or bad. I'm going for a very simple example here because I want to do this with a separate condition thrown on it so you can see the effect of something like a sample size. So I have 26 people who are both young and in good health, 24 people who are both young and in bad health. As for the old, I have 24 people who are old and in good health and 26 people who are old and in bad health. Here, you have been given the overall sample size of 100 and the marginals across each of the 4 intersections here. So you will remember I am comparing the total column, the one you see all the way on the right, which is 50-50. 50% of people in this sample are in 50% are in good health and 50% are in bad health. But if I look at the young, 52% are in good health and 48% are in bad health. Conversely, in the old column, 48% are in good health and 52% are in bad health. So do we have a significant relationship here? The numbers differ, but what does that actually mean for significance in an inferential relationship? So let's run through the steps here. What do you know? Well, I know that I have put age in the columns. Therefore, that is my independent variable. And I have put health status in the rows. Therefore, that is the dependent variable. Okay, so my independent variable age is hypothesized to have an effect on the dependent variable of self-rated health. And I'm doing this using a sample of 100 people, n equals 100, and that's it. I am done with step 1. List your independent variable, your dependent variable, and your n. Hypothesis. The null is that there would be no relationship, and the alternate is that there is a relationship. So put in the language of the variables that I'm operating with here, there is no association between age and self-rated health. That's the null, or H0. And then conversely, H1, or my alternative hypothesis, says that there is an association between age and self-rated health. No association on the null is an association on the alternative side. Good to move on? Great, we are motoring today. So steps 3 and 4, I want to do something different. Steps 3, let's set our alpha level at 0.01. Therefore, you are being asked whether there is a relationship between these two variables with 99% confidence. Now, obviously, if you remember the point of degrees of freedom and the point of a no-tailed test, what that's going to do is make the number that you need to exceed in order to reject the null hypothesis much larger. It's going to inflate outward. Okay, so determining the critical region, we need our alpha level of 0.01, and we need our degrees of freedom of r minus 1 times c minus 1. Now, you will remember that r equals the number of rows. Here, that is 2. And c equals the number of columns. That is, once again, 2. So 2 minus 1 times 2 minus 1, degrees of freedom is 1. Simple enough. So what I'd like you to do is go into your stats packet, Appendix C, and let's look up the variable, or excuse me, let's look up the intersection of a DF of 1 and an alpha level of 0.01. I'm looking at it right now, and what I get is 6.635. Therefore, we must calculate a chi-square in the observed data that is greater than 6.635 to say we have a significant finding or significant relationship at 99% confidence, because we're only giving ourselves, instead of the classic 5% chance of making a mistake, we're only giving ourselves a 1% chance of making a mistake here. I'll pause there briefly to let you guys finish and get caught up if you're a little behind. Okay, so let's get to work. Now we will need to calculate frequency expected, frequency observed minus frequency accepted, and frequency observed minus frequency expected squared divided by FE. So the first step here is to calculate what frequency expected is for each of our 4 cells. And we do that by taking the total percentage and multiplying it by the total raw value in the column. So I can see here that 0.5 50% of everybody in this sample is in good health, high health. I am going to then multiply that 0.5 times 50. Where did I get 50 from? Well, it's the total amount of people that fall into the young age group. Numbers here, you should see a pattern that is going to become very apparent once you actually calculate this out. Okay, so 0.5 times 50 to get to a frequency expected for young and high health. Right? I'll use the cursor here to show you. This 0.5 gets multiplied by 50 down here to get the high health. And then for the old, to get the high young health. And to get the high old health, 0.5 times 50 down here, that then goes up into frequency expected. So I'd like you to, in your notes, try your hand at completing this entire table here. Okay, so I'm going to move forward. Pause it if you need more time, obviously, because that definitely wasn't enough time, I don't think, but just pause it. And for those of you, if we're ready to continue, your table should look something like this. The frequency expected for all cells is 25. The frequency observed minus frequency expected is 1, -1, -1, and 1, respectively. So it's a matter of whether the observed value is 1 greater than the expected of 25 or 1 less than the expected value of 25. Square that and divide by the frequency expected of 25, and the value here for chi-square for all of our cells is 0.04. So the final step then is to sum those four, compare to the critical chi, and then make it a decision. So 0.04 plus 0.04 plus 0.04 plus 0.04. That will then give me a chi-square of 0.16. Okay. So what do we do with that? You will remember, I take that value and I compare it to the critical value with 99% confidence of 6.635. So is 0.16 greater than the critical value of 6.635? It is not even close. So what is my interpretation here? I failed to reject the null hypothesis. And I conclude that according to this data, there is no significant association between age and self-rated health in this sample. Okay. And with a chi-square that low, our critical chi, if we were doing 95% confidence, would have been like 3.84 something like that. 3.84, I don't know exactly, but it would have been 3.8 something. And so even at 95% confidence, we would have failed to reject the null hypothesis. So what are we going to do about this? Well, let's compare this to another hypothetical example. Because as it turns out, the weakness of chi-square is that it can be pretty darn sensitive to sample size, and not always in a good way. I always say adding more data is a good thing. In the case of chi-square, a very, very large sample can sometimes give you a situation where it can sometimes put you in a situation where even very, very minor differences still appear significant. So let's see how that works in practice. What's different about this table? Notice how the percentages of this table mirror exactly what we were operating with in the previous example. 52% and 48% across the good health row, and 48% compared to 52% across the bad health row. 50-50 in the overall population. But the difference here is that my sample size is not 100 anymore. It is now 10,000. So I have added a tremendous amount of data to the sample here. Let's see how that changes what happens for us. So using what you have here, I'd like you to run through this table again and calculate frequency expected, this time by multiplying 0.5 times 5,000 and moving from there. Then calculate FO minus FE, then finally square that and divide by frequency expected. Do that and sum them in order to get the chi-square statistic for this table with 10,000 residents or people. Quick mistake there. I'm sorry. All right, please pause the video if you're not ready to go forward. Here, instead of having, when we just had 100, the frequency expected was 25 for all 4 cells. Now it's 2,500. And so that means that even it's a very minor percentage difference between 2,500 and 2,600 in raw value, that's 100 observations. So frequency observed minus frequency expected becomes, going from left to right, 100, negative 100, negative 100, and 100. Finish out the table, and you have chi-square for each cell of 4. So what do we do with that? Well, when I move forward, I have to sum these now. So 4 plus 4 plus 4 plus 4 now equals 16. So once again, I ask you, is 16 greater than our critical value of 6.635, which is unchanged because the critical value is calculated with degrees of freedom, which are rows and columns, not the raw n. Yes, it is. 16 is way, way larger than 6.635. So even though the percentages did not change, we reject the null hypothesis with 99% confidence, and we conclude that there is a significant relationship between between God, what am I doing today? Between age and self-rated health. Forget about that, please. Yeah, is 16 greater than our critical value of 6.635? Yes, we reject the null hypothesis with 99% confidence, and we conclude that there is a significant relationship between age and self-rated health. What the hell just happened? Let's stop and take stock. Chi-square is extraordinarily sensitive to sample size. So even though the marginals were identical between the two examples, that is to say the percentages in each cell were the same, because we made our sample size 10,000 instead of 100, what that did was push a non-significant finding into becoming significant. And that might be a fake, that's a relic of sample size, of a very inflated sample size. And so given the fact that I personally do a lot of cross-national research, that's a reason why I don't personally do a lot of chi-square. Like I find other things to do here. So chi-square is a great place to start. But when I am often publishing off of a data set which has an N of 40 to 45,000 Europeans across 20 different countries, 22 different countries sometimes. And if you run a chi-square, even when the variables are obviously telling you to do a chi-square, everything becomes significant. And if everything is significant, nothing is kind of significant at that point. Okay, so what we need to do is similar to ANOVA, where we used eta squared in order to calculate the strength of the association. We wanted to know how much total variation was actually being accounted for between the groups. We now need to do a similar type of metric measuring the strength of association. So let me present to you Cramer's V. Cramer's V is the square root of your calculated chi-square divided by n times degree of freedom asterisk, where n obviously is the sample size, and degrees of freedom asterisk is either r minus 1 or c minus 1, whichever happens to be smaller. In this particular example, it doesn't matter. Both R and both R minus 1 and C minus 1 result in 1. So how is this going to work? Well, in our large N example, chi-square equals 16, and the sample size is 10,000. So I will need to take the square root of 16 divided by 10,000 times 1, or the square root of 16 divided by 10,000. That comes out to 0.04. So this, once again, is going to be measured between 0 and 1. 0 is the smallest and weakest relationship that you can have. 1 is the most powerful relationship that you can have. So what I'm going to do here is, depending on our degrees of freedom, I'm going to classify my relationships as either weak, moderate, or strong, depending on where Cramer's V falls within this range of values. So if degrees of freedom equals 1, that means that there's fewer marginals. So the range of values is going to be look different there, and it's generally going to be a little bit less forgiving because there's less data that was put into it. So the range of values here, what am I looking at? Well, if it's between 0.1 and 0.3, that's a weak relationship. So if you think about what we just calculated, it's a very weak relationship. If it's between 0.3 and 0.5, it's moderate. Anything larger than 0.5, strong. As degrees of freedom rises, we will end up being able to determine moderate and strong relationships with lower values of Cramer's V. Notice how moderate now in degrees of freedom equals 2 of moderate. The range for moderate is between 0.21 and 0.35. So compare that to what happened with degrees of freedom 1, and it's easier. It becomes a little easier because there's more data to work with here. But this ends up being a little bit more accurate than simply looking at the chi-square number and saying, yes, this is significant. In a large enough sample, it would be weird. It's almost a weirder finding if things are not significant. That's a bizarre thing. So what about with our smaller sample sizes? Remember what your Cramer's V was for the large N of 10,000. We calculated 0.04. When we had a smaller sample size, let's run through that. The square root of 0.04 divided by 0.04 divided by 100 times 1. Actually, God damn it. You can see I had that right down at a later point. God, I am... you know what? This is a reminder to take more care in evaluating my PowerPoints before I sit down and record. So 0.16 divided by 100 times 1. The sample size is now 100, but DF asterisk is still just 1. So that gives me 0.16 divided by 100, which gives me the square root of 0.0016. Take a second to calculate that. And we have arrived now at a Cramer's V of 0.04. Does that number sound familiar? It should. So because the marginals were ultimately the same, and because we were able to normalize and account for the sample size here, we understand that whether the relationship is significant or insignificant, the sample size and the Cramer's V tells us what the effect of N really is here. It tells us what the real strength of the relationship is. So with a small N, it was not significant. With a large N, it was significant. But either way, Cramer's V worked out to 0.04 because the marginals were ultimately exactly the same. Okay? Now, to wrap this up, let's apply this to our religion and politics example for Monday. So what did we have going on there? Well, chi-square was calculated there to be 38.21, which we then divide by 518, the total sample size, times df asterisk of 2, because rows were 3 and columns were 3. So the smaller of df are df for rows and df for columns. It doesn't really matter. You're going to end up at 2 no matter what there. So multiply 2 by 518, we get 1036. Divide that into the observed chi-square of 38.21, and that gives you the square root of 0.03. Or Cramer's V now equals 0.192. If you remember, you look back to the table. We're operating with degrees of freedom of 2. This is a sort of a weak but approaching moderate association. It's pretty darn close to moderate, actually. So you can see how in a situation where there was more of an effect of the independent variable on the dependent variable, we're able to show here that, yeah, the strength there is something worth talking about, where even though the 10,000 person sample did produce a significant chi-square, it's probably not really worth our time thinking too much about that. And it's also would be weird to see that there's almost no difference between the self-rated health of the young and the old. That just seems sort of weird to me. So yeah, it's almost like somebody came up with those numbers in order to prove a statistical point. What can you say? So you will be turning in a homework to me once again on Friday morning, no later than 10:30. In that, I will expect you to do all 6 steps of the hypothesis test. I will expect to see you calculate Cramer's V for that finding, regardless of whether it's significant. Cramer's V can always be calculated. It doesn't really matter whether significance is found or not. You always want to understand what's the actual association between the two variables here. Okay, so chi-square is not terribly complicated. If you need practice, I encourage you to practice. If you need help, I encourage you to reach out and seek that help from me. But I also think it's pretty easy to grasp the process here. Calculate frequency expected first. Let's go back to our table. Calculate frequency expected first, then subtract that from frequency observed, then square that, and then divide it by the expected frequency. That will give you the chi-square total for the cell that you're working with. Do it for every cell, and then sum the chi-squares of all those cells, and you get chi-square. Again, it's some wrench work, but not terribly complicated in its logic there. All right, so I very much look forward to seeing those homeworks come in. I was very pleased and very happy with how people did on the ANOVA problem, and I encourage you, and I hope that you keep that up, and I encourage you to keep that up. That's what I got for you today. I'll be back on Friday with a homework or review and maybe some more interesting things to talk about as well. Thank you very much, and you guys take care of yourself. Keep working hard and keep feeling good.